Welcome to Chapter 1, Part 1. We're going to go through on this video 1.1 through 1.3. That'll help you with the homework, the Part 1 of Assignment 1. So the Part 1, Section 1 just deals with kind of putting things in a little bit of perspective. So looking at our place in the solar system. Earth, it's just an average planet around an average star in the outskirts of an average galaxy. Part of our bigger universe there. So the universe can be described many ways, but basically it's everything. The universe is everything. All of space, all of time, matter and energy, everything is the universe. So in chemistry, those folks that have chemistry in the past, you might have learned about the system and the universe. The system is what you're looking at. The universe is everything else. Well, in the astronomical point of view, the system would also be part of the universe. So what is astronomy? I think most people are in here and understand that astronomy is basically the study of everything. Study of the universe, study of stars, study of planets, how they form, how stars form, how they progress, how galaxies change. And part of understanding the astronomy is understanding the sense of scale, the sense of size. We're a bunch of really small things in a really, really large galaxy. Which is also part of a really, really large universe. So we're going to be dealing with really, really big numbers in terms of distances, in terms of sizes of things, in terms of numbers of things. So in order to deal with really, really large distances, we use a measure called the light year. And a light year is a measure of distance. Big misconception is light years measure time. No, the light year is just defined as the amount of distance light travels in a year. It turns out to be about 10 trillion miles. Tremendously large size. The Earth-Sun distance is a little under 100 million miles. So this is many times or many orders of 10 magnitude bigger is a light year. It takes light about 8 minutes to get to Earth from the Sun. So for a large part of our history and our prehistory, we thought of Earth as being at the center of everything. And if you think about it, if you go back without somebody telling you that we're not, just by doing basic observations, it's really easy to come to the conclusion that we are the center of things. The sun rises in the east, sets in the west every day. Same with the moon. We see the stars change in their position with respect to the horizons, but not with respect to each other. So it's very easy to put us at the center of things, with everything revolving around us. But the more we've studied, the more we've looked at things, and for pieces of evidence that we'll learn about later, we'll find that our location is really not very special with respects to the solar system, the galaxy, or even the universe. So we're not central to any of those. In fact, if we were at the center of our galaxy, it would not be a very fun place to be. So to kind of put it succinctly here, we're just one of 8 planets orbiting an average star near the edge of the Milky Way. It's our galaxy, and our galaxy is just one of billions. So there's a lot of stuff out there. To put it on a sense of scale, our galaxy, this is a picture of a galaxy that's similar to our Milky Way galaxy. Because of the sizes of things, there are no pictures of our galaxy from outside of it. But this galaxy we think is pretty similar to ours. This is a galaxy that can be seen in the constellation of Ursa Major, or the Big Bear, or thereabouts, the Big Dipper. And this one represents a distance across of about 100,000 light years, which means for a star that's shining over here, that light to travel across the distance of this galaxy to another star over here would take 100,000 years. That's not even counting the amount of time it takes the light to reach our galaxy. So here's a little a video. Let's see if this will allow me to play it here. If not, I'll put a link in the description to this video. Let's see if it'll let me. I don't think it will. But there's an embedded video in here, but we'll show you this. This kind of puts things at the sense of scale. So this video is going to show a zooming out from Earth into the farthest reaches of the galaxy. and beyond the galaxy into the farthest reaches of the universe. And it really gives you a sense of scale. It's going to travel well faster than the speed of light, or else you would be here for a very long time watching this. Section 1.2 talks about scientific theories and scientific methods. It wouldn't be a science class without a quick little discussion of these sorts of things. So when we use the word theory in science, we don't mean theory like you would say if you got home today and noticed that the door was kicked in, the cushions were all strewn about, drawers were open and the contents spilled out. You might say you've got a theory that your house was broken into. You don't know for sure, but you got a hunch. All the evidence is pointing towards that. A theory in science holds much more weight to that in terms of how much faith or how much confidence we place in a theory. So some common theories, the theory of gravity. We're pretty sure if we step off a ledge, the theory of gravity states we're going to come crashing down. Theory of evolution by natural selection. All of these are very well tested theories, and that term there, tested, is kind of a defining characteristic of theories. So all theories must be testable. So they must make predictions. Those predictions can be put to a test. Those tests, depending on how the outcome, can either strengthen or weaken a theory, but theories are not set in stone. They're very, very close to true, but new evidence is always shaping them. The last couple of bullet points here with them being simple and elegant, they are not necessary to be simple and elegant, but it's nice if they can be. So if they can be summed up in a couple of sentences that are understandable to common folk, it's going to be easier to spread. They can be proven wrong, but never can be proven right 100%. You really can't. The way science works, you can't really do that, right? So, for instance, I like to say, can you prove to me that that unicorns exist, right? You can't prove the absence of them, right? So you can't say for sure that they're not there. We haven't found any. To the best of our knowledge, there isn't, but all it takes is finding one unicorn to disprove that. So another way to look at it, I think of like a theory as like a piece of artwork. Early on, as the artist is working on it, you kind of get a general shape, general outline of what they're painting or what they're sculpting. And as time progresses, with more work on it, the finished or the ideal view of what it's supposed to be becomes clearer. Same with science. The more early theories are pretty simple, but they can be refined through testing, and we're still testing a lot of our theories. So how does it work? Well, the first thing you need to do to come up with a theory is to make an observation. So once you find an observation, you try to come up with some idea explaining it. A lot of people would argue that first explanation would be a hypothesis, but once we've tested that hypothesis, we can create a theory that explains that. Once that theory that explains it is well thought out, well described, we can come up with ways to test that. We can make some predictions. And we can see how those predictions can either come true or don't. We might have to go back to the drawing board. And then the last part of this chapter is what we call the obvious view. Obvious being not self-evident, but obvious if you go outside and you look up at the sky, what do you see? And to the right here is a picture of the constellation of Orion. Really early in the morning, you might be able to see this if you're waiting for your bus in the dark. But it'll become more apparent as we get towards winter. This is the hunter, Orion the hunter. And the obvious view is just all about simple observations. You're looking up. At any one time, depending on your conditions of light pollution, you can see about 3,000 stars, which represents a little bit less than 1% of the amount of stars in our galaxy. And they're distributed relatively randomly, but our brains are really good at connecting dots and seeing things where there aren't necessarily things. And different societies have come up with different explanations for the patterns of the stars that they see in the sky. So this is constellation of Orion, these stars here. This is a star in the shoulder and another star in the shoulder of Orion. And some stars are represented by the knee and the ankle of Orion. And one of the very common things that a lot of people can identify in the stars is Orion's belt. And then hanging from the belt, we've got a couple of stars that make up the Sword of Orion. So there are some common constellations out there that are easy to kind of spot, that are somewhat important for navigating our way around the night sky. Some more than others. So one of the most important stars with respect to navigation of people up until the middle part of the 1900s, before we had really good charts and before we had GPS technology, was Polaris. Polaris, if you drew a line straight up out of the North Pole, you would eventually, that line would be pointing to the star Polaris. So where we are right now, it never sets. It's always above the horizon. And since we know where it is at all times, it can help us figure out our latitude, how far north and south of the equator we are, or how far, you can't really see it from south of the equator, but if you're standing on the North Pole, Polaris would be directly overhead, so it would be 90 degrees above the horizon. If you're standing on the equator looking north, Polaris would be right at the horizon, or 0 degrees above the horizon. So these constellations are useful, but they also sort of can be caught up in some uselessness, and that's astrology. All we're going to talk about astrology comes from this slide, but basically the ancient astronomers started as astrologers, just like the ancient, or the predecessors to chemists or alchemists. So the astrology makes these predictions about different people and personalities based on the patterns of the stars and the moon and the sun that existed when you were born. So you look up in the newspaper and you find out your birth dates, and you find out your horoscope. That's the work of astrologers. But horoscopes are written very broadly. Characteristics are written in such a way that you can maybe make the case that they can pertain to anybody. The fun thing with them is if you get a couple of different newspapers, and on any given day, they're going to have different horoscopes. So they're really careful about making specific predictions. What we have here is a nice, if you were to take a map and turn it inside out, right? So this is looking up from the night sky from every point on Earth. This dotted line here, this is the ecliptic, not that line there I just accidentally drew, but the ecliptic is the path that the sun takes through the night sky, or not the night sky, because it wouldn't be night if the sun were out. And these are all the different stars that we can see, and they're grouped into areas of patterns, so those patterns become our constellations. Just like a typical map, as you reach the poles, there's great distortion. So for instance, if you look at the North Star, this is Polaris right up here, part of the Little Dipper. Little Dipper looks huge here, but Little Dipper is actually pretty small. The Big Dipper is over here. Some common constellations that you can see. Here's Orion the Hunter, a little bit south of the ecliptic. And then there's because most of these civilizations that named these were found in the northern hemisphere, the northern ones have those names and ties to Greek mythology. But then in the southern hemisphere, these were named in much more modern times. So you get things like the telescopum, named after the telescope. You get another one somewhere in here about the microscope. So they're not really as involved in Greek mythology as the more northern ones. So if we're looking from Earth at a particular constellation, this one here happens to be Orion, the shoulders and the belt and the knee and ankle there. They appear like they're the same distance from each other, or from the Earth. So that gives rise to this notion of the celestial sphere. So the ancients used to believe that the night sky was just basically a glass dome overhead that had some holes poked in it and allowed light to filter through. So to the ancients, all the stars looked like they were the same distance away. But if we were able to travel outside of our limited point of view, we could see that the stars that make up Orion vary greatly in their distance from Earth. So from other points in space, the same patterns wouldn't be able to be seen in the night sky. So if you were to land a craft on another planet much more distant from our solar system, the night sky would look different. There wouldn't really be any identifiable patterns. There might be new patterns that you can come up with and new constellations, but the same old ones wouldn't be there. You'd still maybe see the same stars, but you'd be seeing them from a different angle. This is another video that didn't import to this, but I'll put a link to this one here. But it's just basically, it's doing the same idea. We're taking a look at one of these constellations from Earth, and we're kind of walking to the side of it, and we're seeing how those stars align themselves. So, to mention the celestial sphere, good way to look at it here, we've got Earth in the center, and just imagine it some distance away, it doesn't really matter how far away. You've got this glass dome surrounding the Earth. And in that glass dome, on its surface, are where all the stars are found. It's not the case, but sometimes it helps to figure it out, but to look at it that way. The stars are so far away from each other and traveling so slowly with respect to each other that their positions with respect to the other stars in the sky seems pretty fixed. So they're pretty much unchanging. Because of that, we can use a coordinate system to help figure out the locations of stars. And we'll do a lab this week that relates to that, where we deal with, on a map of Earth, you would deal with longitude and latitude to find a particular location. On the map of the sky, we use declination and right ascension, or altitude and azimuth. So different ways to plot our way around the night sky. Last one here, this is another showing the celestial sphere. Unfortunately, I'll have to put a link to this one in the video as well. So that should wrap it up. Don't let this be a substitute for reading the chapter, or at least scanning through it. Definitely want to have the book on hand when you're answering the questions in the on the Mastering Astronomy website.